Testing, testing 1, 2, 3. All right, let me just make sure we look good. That looks good. That looks good. All right. Again, my name is E.J. Daigle, Dean of Robotics and Manufacturing here at Dunwoody College Technology, and I'm going to do an introduction to the Logix 5000 platform. Included in the Logix 5000, there's a number of different processors. You know, we have ControlLogix, CompactLogix, several processors within each variety, along with some more flexible type of I/O and things like that. But really, what this is particularly aimed at is going to be the CompactLogix hardware and the RSLogix 5000 software. So here we go. All right, so first off, in our lab, we use the 1769 CompactLogix hardware. As you look at this, the great thing about the CompactLogix is it combines kind of the best of both worlds. You know, if you come from like the RS500 platform, a lot of times you're kind of confined by a MicroLogix not being expandable or having very limited expansion capabilities. And in some cases, you know, you had the great expansion capabilities of the RS500 platform, but you had to kind of know what you wanted. You know, do I want a 4-slot rack, 7-slot rack, or something larger than that? The CompactLogix is nice because it's exactly that. It can be very compact, but it is also expandable. So as you look at this, you'll see a CPU right here, and then you'll see kind of a bus terminator on the end right here. Next to that, we have our power supply. And then we have a number of different I/O modules, module 1, 2, 3, and so forth. But by basically removing this bus terminal and adding an expansion module right here, and then putting the bus terminal on the end here, this thing can expand out to a 4th, a 5th, however many modules, to an extent, however many modules I need that thing to be. So it can be larger, it can be smaller, it can expand in, expand it out. It's kind of like an accordion almost in how it moves in and out to meet the requirements of the application. So a little more detail about what we were just talking about. First of all, some nice things about the CompactLogix hardware. It has specifically for our 1769 L32E, you'll see we have both Ethernet IP and we have RS-232 communications. Some people might think, well, do I really, if I've got Ethernet, that's good enough, right? Well, and it is to a certain extent, as long as all your other devices are Ethernet. Perhaps you've got an older drive or an older HMI that can talk just fine over RS-232 to the 1769 L32E, but you don't want to spend money on that new HMI or that new drive, so you could maintain the Ethernet capability with some of your devices while maintaining the RS-232 capability where you need it. All right. Another nice thing is we can DIN rail mount it or mount it directly on a panel. I think everybody understands the idea of DIN rail mount, but also these little holes allow you just to panel mount it. So if you just want to screw it straight to a wall or straight into a panel, into a backplane of a panel, you can do that. I don't recommend doing that. I would just say DIN rail is so cheap nowadays. You ought to put everything on DIN rail. They even make DIN rail switches and DIN rail power supplies and DIN rail everything as far as what you would need. So there really is no need to deal with panel mount. Excuse me there. All right. The next thing here is we talked about it being kind of like that accordion style. It can expand out. The limitations here is we can have up to 16 I/O modules. So think for a second, if you go 16 modules, each one of these modules taking up, this amount of space. Yeah, this thing gets pretty big pretty quick. 5, 6, 7, all the way out to a 16th expansion module out here. So that's a lot of expansion that you can do with this, which is terrific, because you don't have to. You don't have to buy a 16-slot rack to get 16 modules. You don't have to buy a 4-slot rack to get 4 modules. You can buy one CPU, the bus terminators, the power supply, and then however much I/O you want. If you want to expand it out later, you just do it. The CPU. specifically the power supply. So when you look at that last slide, you'll notice the power supply is sitting right next to the CPU. That's pretty traditional for what we do. You can locate that power supply over here, and put, IO module 1, 2, and then the power supply if you want. I don't recommend that. It's the only rule is that the CPU and the power supply have to be within 4 modules of each other. Okay. As you get further and further away, the reference voltage is very important. Potential noise, I'm not that worried about it, but really the reference voltage and the CPU having a clean, crisp, reference voltage to operate off of is important. So I just recommend putting the CPU and the power supply right next door to each other. There's a compact flash card which provides non-volatile memory backup. It's not required. The other thing that's nice about this compact flash card that goes right here is if you, let's say you want to get a program onto your CPU. Maybe it's I don't give an example. Maybe you're putting this PLC into a car wash or something like that, and it's the same car wash every time. So rather than going in and having to program every PLC with the same car wash code every time, you could have that car wash code loaded onto a compact flash card, and as you install the car wash, you could boot up your CPU and pull that code right off the compact flash card, because we know we've got what we need and we don't have to program every single time because it's the same program. And then those in caps that we talked about really they're kind of bus terminators or bus ins. So one will go down on this end and one will go down on this end. But they basically, because these modules link together, with a little cable in between them that you kind of slide connect, there has to be one on the end to kind of terminate that bus at the end of the line. All right, a little bit about the 1769 CompactLogix I/O modules. So you got an example here of a DC input module. So 24 volt DC sinker source module. You can see I have 16 points of input here. So I've got point 0, point 1, 2, 3, 4, 5, 6, 7, all the way out to point 15. They make these modules in a number of different varieties. So I can get an AC input module. I can get a DC input module. On the output side, those would be my digital guys, right? So digital meaning on or off. 24 volts DC typically is what you're going to see on all of this stuff. I can also get, well, excuse me, that was an AC input module, right? So that's going to be 120 volts AC. DC and AC. I can also get an AC output module, which is 120 volts AC. Or I can get a DC output module, which is 24 volts DC. I can get a relay output module. The relay output module is extremely popular. Why? Well, because unlike the AC output module, where I'm kind of confined to an AC voltage or a DC voltage for the DC module, the relay output module, I can choose what I want it to be. Maybe it's AC, maybe it's DC, maybe I need a bunch of each. And it's not limited to a particular voltage either, right? Let's say I want to switch 12 volts AC. That relay output module is going to be the perfect solution to that. Then you have an analog input module and an analog output module. Similar to other PLCs, we're looking at a 0 to 10 volt DC signal, or in the case of a current signal, a 4 to 20 milliamp signal. You can do a differential as well on this, so you can do a negative 10 to a positive 10 volt signal if you want. So there are a lot of different options that you have. Of course, there's a lot of different I/O modules that you have too. There's certain specialty modules. There's stepper and servo modules and different things that allow you to, maybe work with temperature devices, thermistors, or RTDs. So there's specialty, but these are kind of your traditional I/O modules that you see on all of our PLCs. So 1769L32E processor. So when we're talking about the processor, this is the guy we're going to talk about a little more in depth right now. So that's 1769L32E processor. If you look at the 1769L32E, obviously you have your Ethernet port, and you have your RS-232 port, and you have your compact flash port. We kind of mentioned all of those a little bit already. What we haven't talked about is this guy right here. This is your key switch. When you get into the lab, these will always be left in remote. The reason being is when you're in remote mode on the key switch, You can upload, download, you can switch it between, remote programming, run, program. You've got complete control from the Logix 5000 software. So we just leave it in remote mode for that reason, is we have complete control. When you're out in the industry, more common for this key switch to be left in run and for the key to be removed, where a maintenance person or a controls engineer would be in charge of all the keys for all the processors. In run mode, basically the CPU is going to execute the current ladder diagram. The outputs are enabled. You cannot program in run mode. You have to take the CPU out of run mode to program. So just as a security precaution, by putting it in run mode right here, right, the key switch in run mode, removing the key, really the operators, all they can do is just run the code and make the parts, right? When someone wants to program it, like a controls engineer or a technician of some sort, they're going to have to get the key and position that key switch into the program mode. Now in the program mode, some interesting things happen. In the program mode, we disable the outputs, and all we can really do is upload and download the program in program mode. So one of the dangers of the remote mode is you are controlling the mode of the PLC from a particular laptop computer. The reason why some people are, why there's a little bit of concern with that is if you go ahead and put the PLC into run mode via the software and somebody's got their hands in the machine and something turns on, I mean, there could be some danger to that versus being out at the CPU and switching the key switch from program to run as needed, and making sure everything's clear before you do it. Because remember, with Ethernet, it's possible that I might be talking to this PLC, from a control room, from another location completely. Theoretically, I could be VPNing in from home and logging into this PLC and looking at I/O, and if I'm in remote mode, I could even change its mode of operation from program to run. So just keep that in mind. In the lab, we're never very far away from our PLC, so we'll always leave them in remote. And to be honest with you, the reason why we leave them in remote, we just don't want to lose the keys. So we got all the keys in the instructor desk, and if we do lose a key, we can still program. The indicators, I will tell you right now that when it comes to troubleshooting PLCs, these are amongst some of your most important troubleshooting tools. Both the indicators on the CPU and the indicators on the I/O modules. Without these indicators, they are essentially like little multimeters that are telling you what's happening. Yep, I'm good. No, I'm not good. So as an example, your run indicator, which is right up here, your run indicator, if it's off, essentially you're in program mode. And if it's steady green, you're in run mode. It doesn't mean the key switch is in program or run, because remember, the key switch could be in remote, in which case the mode run or program is controlled from a laptop computer running the software. But off, you're in program mode. Steady green, you're in run mode. The force indication, so you can see the force indicator right here. If it's off, that means there's no I/O or tag forces installed, so nothing is trying to force an input or output. Again, remember what a force is. A force is essentially using the software to turn a bit on instead of letting the logic determine what bits are on. So the software, it's great for troubleshooting. I want to turn this bit on and see if it actually works and see if everything's working, but it can also be dangerous, right? So that's why we have this force indicator. Typically, we want to see that force LED off at all times. That means no I/O or tag forces are installed. A steady amber, and they make this a steady amber, both steady or flashing, so it kind of stands out. You get a lot of green indicators on your CPU module, and you occasionally get a red indicator. Amber indicators are a little bit unique. They don't necessarily stop the program from running. They're not necessarily a critical error. However, you want to pay attention to them, right? Because a steady amber indicator means there's an I/O force active. And I don't know how many times I've seen somebody playing with forces in the lab or out in the industry and forgetting to remove a force, and then at some point in the process something goes haywire, and they're like, why isn't this working? Only to discover when you open up the control cabinet, look at the CPU, you see that there's a force installed. And it's real easy to go into the 5000 software, hit remove all forces, and you'll be right back to where you need to be. But they make these amber for a reason. And the two versions, steady amber, there's an I/O force active. There's something overriding a bit right now. Flashing amber means there's a force installed, but it's not enabled. So we've basically said, you know what, there's a force in here, but we're not going to enable that force. So it's not controlling the logic right now, but it's important to know that it's there and it could control the logic. The battery indicator, so as you look at this, the battery indicator is right here. If it's off, that means there's a battery installed, the memory is backed up. If it's steady red, that means the battery is missing, or it's low voltage dead state, something like that. Remember what the battery is for. You don't lose your logic from the battery per se. The things you do lose, though, are things like date and time. So if you're dependent at all on a real-time clock, so you want to know, every 30 days or every 15th of the month or something like that, you want something to happen. You want somebody to go change a filter, some maintenance indicator comes on or something like that. It's important to keep those batteries alive. I've been in plants where those battery lights are lit and the system's running and nobody cares. And that's fine, as long as you're not dependent upon that battery doing some critical backup to your system. The I/O indicator, which is going to be over here. The I/O indicator off means I/O is not configured. Steady green means the controller is actively communicating with all I/O. This is the one we want. Flashing green means that one or more of your I/O is not responding. Might be that you don't have a particular I/O configured, or it's having trouble communicating. You have a wrong revision of a module or something like that. Or flashing red. That means we have controller I/O that's causing us a major problem in the system. All right, and I didn't go over all of these, but these are going to be your critical ones that we're worried about the most. And so then the RS5000 data types, very similar to what we've done with other PLCs. Our Boolean data type means a 1 or 0. So they kind of do this neat little graph in the RSLogix instruction manual. A Boolean is a single bit, and it can be on or off, and that's it. A short integer is going to be 8 bits, so from 0 to 7. And if you do 2 to the 8, you can kind of get where this number comes from. 2 to the 8 is 256. And so we can go from negative 128 to positive 127. An integer is going to be out to bit 15, so it's 16 total bits, bit 0 all the way up to bit 15. If you do 2 to the 16, you get 65,535 or 536, one of the two. And what's more important there is, actually it must be 536, is that it goes from negative 32,768 all the way up to positive 32,767. Sometimes people ask me, well, why is this a 7 and not an 8 if this is 256 and if this is a 6? Well, the reason why is because, remember, 0 counts. So we care about 0. So our positive side, 0 becomes kind of a part of the positive numbers is what it really does. A double integer, if you do 2 to the 32, you'll come out with a really big number, something like 4.3 billion. I'm not going to write the whole number out. But if you put a sign on that, you get negative 2.14 billion, all the way up to positive 2.14 billion. And then our real data type, which can go from a very, very small number to a very, very large number. So you'll see the negative, all the way up to the positive here. And what they're really showing here also is it can use a lot of decimal places, right? So we can go out a lot of decimal places on this thing as well. I don't worry about trying to detail all these things out. Nobody's going to remember these exactly. What is a real? A real is a decimal number. That's the big difference between everything we've just looked at is all of these other guys up here, from here to here. These are all going to be integers. Be careful there, right? Those are integers up to here, right? They're short integers, they're double integers. This guy here is just a single bit. The bool is just a single bit is all he is. And then when you get down into the bottom down here, this is where you're going to have your decimal numbers. So some interesting things about the RSLogix 5000 data types. You can define your integers, your floats, your counters, and your timers, but you can define them as arrays, which gets kind of, get people a little bit confused here, right? But it's an array of a certain amount of elements. So if I call this my counter array, right? My counter array is right here. And my counter array, let me write him out what he actually looks at, like, is he's got the first index. The first index has 2 elements, so he's an index of 2 elements. The second one has 3 elements, and the third one has 4 elements. So 2 times 3 is 6, 6 times 4 is 24. So this would be 24 counters that I could use using this array. I don't know that I'm the hugest fan of this guy, and you can see the 24, right? You got 3 here, you got 6, 9, 12, and then you got 2 layers because you got a set down on the bottom here too, right? So you have 24 counters. You know, it's great. You can get really, really big, right? Could you do counter, you know, 255, 255, 255? Yeah, you could. How big does that thing look? I'm going to draw it real small. It's going to have a lot on the front, right? It's going to go this way. It's going to have a lot here too as well, right? And a lot here. So this thing's going to get crazy. It's going to be like a Rubik's Cube that has 255 squares on every single side. But, you know, let's talk about what would it mean if I wanted to get a certain element out of here. What would it mean if I wanted just this little element right here? Which counter is this guy right here? Well, we know that he is he in the first index? Yeah, so he's in the first index. So he's counter, right? Because the first index is this top layer here. So he's counter 1. Okay. Then I got to figure out, okay, the second index is here, right? So that goes here, here, here. He's in the third index. Is that right now? Yeah, counter 1. He's in the third index. Okay, because he's in this kind of row over here. The second index, third element of the second index. Yeah, let me rephrase this, right? This guy is the first element of the first index, which puts him in this kind of top layer up here, right? And then the second index is going to be going this way, and I can see he's kind of in this index here, right? That goes back, and then I can see where is he in the third index. Well, the third index heads back this way, 1, 2, 3. So he's going to be element 2. So that counter element guy right there is going to be 1, 3, 2. Now I'll be completely honest with you. I don't use these at the array level very often. I usually, when I define these, I define my counters as you know, maybe 255 in the first index, and then 0 and 0. I don't even use the other indexes. That way, when I define a counter, I have, you know, counter 1. The other indexes don't matter. The next counter would be counter 2. And part of the reason why I do that and I don't use these other indexes and set it up as this 3-dimensional array is because I do utilize some hardware in the lab, the Maple Systems HMI, which doesn't deal well with the 3-dimensional array. And frankly, the other reason why I don't use a counter array this big is because it's very rare that I ever need more than 255 counters. So that being said, I tend to just define the first element and leave the other elements alone as zeros. So then it's just counter 1, counter 2, counter 3, you know, and so on. So I don't need 8 billion counters, because I don't know what that is, but 255 times 255 times 255, that would be a whole lot of counters, is what it would be. You know, standard programming languages for RSLogix 5000, these are your standard languages, your relay, ladder, logic, structured text, and function block. Function block. So it's IEC 61131 programming languages. So they are compliant with IEC 61131. When it comes to tagging, one interesting thing about tagging is there are no fixed tags requirements. So just like in the world of timers and counters for these array deals, there are no, you know, set sizes on the number of timer addresses you can get, because you can define whatever size array you want. There are also no fixed tag requirements. So when we talked about the SLIC 500 as an example, or the RS500 platform, when you dealt with the RS500 platform, you were kind of fixed, right? Timers were T4, counters were C5, integers were N7. And you could create additional data files, no doubt, but these were kind of predefined for you. And if you created another data file, it followed that structure, right? You might have a, you know, I don't know, a timer, a T16:0 timer. Well, it still had to follow that fixed structure. When we got into the Siemens S7-1200 and the TIA portal software from Siemens, you'll notice what happened was Siemens predefined the tags as data block 1, data block 2, data block 3. And then we really were creating alias tags for those data blocks. The data blocks were predefined, and then we created an alias tag so that it meant something to us. So we could call the timer, 10-second timer or case counter or something like that. But it really was tagging itself to that data block. And then we could do the same thing with our memory addresses in Siemens as well. I lost my little deal there. There he is. If I had a memory word, MW0, MD4, I could create an alias tag to stick on the top of that. But really, the PLC itself was looking for the actual data tag that it used. It was better than this, right? It's a little cooler than this, but still different than this. Now we're into RS5000, and now we get another feature here. So in RS5000, looks like I wrote 5900 here. RS5000, this is completely user defined, both on a base tag level or an alias tag level. So I can call that timer anything I want. I call it timer 1, and then what I'm going to get is I'm going to get something that looks like this, timer 1. And depending on how many elements I create, if I want timer 1, element 2, so this is kind of strange, right? Because I'm calling it timer 1, element 2. There could be a timer 1, element 3, and there of course could be a timer 1, element 1. So I might not use that timer 1 thing as my deal, unless I was only creating a single 1 by 1 by 1 array, and it was just timer 1. And I could do the same thing with counter 1. I could do the same thing with integer 1. I could do the same thing with real 1. I really am defining that data block or that data file with my own user definition for that tag. There's some concerns about scope. I saw this happen in the lab just the other day. We had a person that was working on a Maple HMI. So it was a Maple HMI and was working with the RS5000 platform over here. And had a bit or something, and these two were communicating over RS-232, and there were some tags in here, and this particular person had the tags at the program level. Now what you'll notice when you start programming in RS5000 is there's two different levels. There's controller tags and program tags. Controller tags can be seen everywhere across all programs. So when you look at this, like controller tag 1, 2, 3, I've created them at the global or controller scope. By creating them at the controller scope, I can pass them from program A to program B. I could pass them between HMI and PLC. I could pass them all kinds of things. Versus creating local tags. Program tags are at the local scope. What that means is I cannot exchange data for tag 4, 5, and 6 over to this other program. And again, these other programs could be, subroutines. These other programs could be programs running on HMIs, drives, other PLCs. So it's very important, if I want this data to be used outside of my controller or even outside of my program scope, then it's important that I tag them at the controller level. Now your I/O tags, like your input and output modules, they're always going to happen at the local tag level. But you can also create some other tags that will reference them, some alias tags that you can reference them at the controller level if you need to. All right, a little bit on timers and counters. So RSLogix, jumped ahead there. RSLogix 5000 timers. I'm not going to get into the details about this. I hope everybody knows what an on-delay timer is. When your enable goes true, your timer is going to start timing at that point, right? That's when it starts timing. Your time T is going to be here, and this would be your on delay, right? That would be your on delay. I wait time T to turn on. So this is essentially what's happening with my done bit. And then when my enable goes away, my done bit turns off. On delay timer works the same as it ever did. The off delay timer, this is the one that still trips people up occasionally. Remember how the off delay timer works? When the enable goes true, my done bit goes true immediately. when the enable goes false, that is the point where I'm going to start timing. So this would be time t. And whatever that preset value is set for, I'm going to delay turning off the done bit for a certain amount of time after the enable goes false. But the trick on this is enable goes true immediately. The done bit goes true. And when the enable goes false, I wait a set amount of time. Again, the retentive works identical to the on delay timer, except for the feature where it doesn't reset. And the reason why is the way the retentive works is I can enable it for several lengths of time, and those can all accumulate with each other, right? I can add these all up, and when I get to the point where I've reached the done bit, it turns on. Now remember, with the retentive, you'll need a reset instruction, a separate reset instruction to reset the done bit. So my enable is cumulative up to my done bit. So if this is, if I need to time for 10 seconds, and this was 2 seconds, and this was 5 seconds, and then this was my link doesn't look right here, but then this was an additional 3 seconds, right? That gets me to my 10-second time. Even though it went off in between, it accumulates and then eventually goes. But I do need a reset instruction because it doesn't turn off with each enable going false. Note here, all of our RS5000 timers have a 1 millisecond time base, but we are 32 bits. Okay, so we are double integer. And what that means is we have 4.3 billion combinations. Now on a timer, we're going to be limited, just like on a counter, we'll be limited to 2.14 billion as our maximum number that we can put into the preset. And if anybody's wondering what does that mean as far as how much can I time, well, if you take, we'll always be in milliseconds. So we will always be in milliseconds. That's another interesting note here. Time base for RS5000 is 1 millisecond. You get no choice to make it, 100 milliseconds, 1 second, or any of that stuff. The time base is 1 millisecond, but you get a much larger preset. So that means if you take 2.14 billion, you multiply it by 0.001, which is really what our time base is, 0.001 seconds. Then we would get 2,147,483 seconds. And if you do the math on that guy into minutes and hours, it's about a 600-hour timer. It's way more than you ever need. If you need something more than that, you probably, you could daisy chain timers together, but you probably need to be looking at the real-time clock or something like that for information instead of using on-delay timers. Count up counters, the exact same story here, right? We're limited to that preset max is going to be equal to 2.14 billion. Okay, so just keep that in the back of your mind. But it's also our preset min, right? We can also go negative on a counter as well. That's why, so you can go negative 2.14 billion as well. We can count up, we can count down, we count up and down. If you ever want to count up and down, what you need to do is you need to address the up counter and the down counter to the same address. And whenever I flip this switch, on and off, the accumulated value will go up. And whenever I flip this switch on and off, the accumulated value will go down. But they will reference the same counter 1 accumulated value. So interesting there, right? We want to keep that in mind here. The reset instruction looks similar to what it did in other ones. I could put a reset instruction somewhere here. I could reference it to this counter 1 and reset it. That's always my preferred method for resetting counter. You can move numbers into presets and accumulated values. Moving is much more common with the accumulated value, meaning maybe I want to start at a certain number because I know there's X number that are going to get left behind every time or something like that. There's so many in the queue. I want to move a value in there. That's the time to use move. There's a big warning down here. Moving a 0 into a counter or timer does not reset the associated done bit. So I've had students over the years and folks in industry that have tried to move a 0 into a counter or timer thinking, oh, I'll reset it that way instead. Danger. A reset instruction will reset both the accumulated value and the done bit. A move only changes the accumulated value. It will not change the status of the done bit. So just because the accumulated value shows 0 doesn't mean the done bit will turn off. So just keep that in mind. Use the reset instruction instead. Example 1, I got a couple of real short examples here for you guys. Just a quick question here. Which data type would be associated with each of these? So we've got an accumulated value. Now remember, we typically in RS500 we think, well, that's an integer, right? Well, in this case, that's a double integer. Why? Because we can go all the way up to that 2.14 billion number, right? How about a timer.dn? Well, remember, a dn is a done bit. A done bit is either on or off. That's going to be a Boolean. Counter preset. Preset's a value. Again, can be all the way up to 2.14 billion. That's going to be our double integer. And then a timer. Oh, good note here. I like that fact that we got the TT. Remember, we do have a timer timing bit as well. Anytime the timer is actively timing, this bit will be on. So if the enable is not enabled on a non-delay, timer timing is not true. Once the done bit turns on, the timer timing bit stops. So if you look at, let's say, the TON as an example, you know, when I do enable bit here, right, and I have my done bit, which waits a set amount of time before it turns on, and then it turns off when the enable goes away. This is really the amount of time that I'm timing. Our timer timing bit will only be on in that time where we're timing bit. Once the done bit turns on, the timer timing bit goes away. Well, and by me saying the word bit over and over again as we talk about this, we must know that that's a Boolean as well. Example 2, just a real quick little review of timers, just looking at it from the RS500 or 5000 platform here. If limit switch 2 is on, which LEDs will be illuminated? So let's say we turn on limit switch 2. So this is on. Our preset's 180. Now be careful here. Let's talk about what 180 is. That's 180 what? That's 180 milliseconds is what it is. So when my limit switch 2 is on, my timer timing bit should turn on, turning on light number 2. If I have not reached the done bit yet, then light number 3 will be on as well. So in this case, 2 and 3 should be on. Now it's asking me if limit switch 2 is turned off. Oh, hold on a second here. I didn't notice something here. This is not an on delay, is it? This is an off delay timer. So if I turn on limit switch 2, am I timing yet? Absolutely not. Remember what the off delay timer does. I messed this one up for you guys here. An off delay timer, when the enable goes true, the done bit turns on immediately, doesn't it? So if the enable is on, if the limit switch is on for the TOF, the done bit's on as well. Timer's not timing. Done bit's on. There's no lights on for this first one. I was treating it like an on delay. I apologize for that. This is actually an off delay timer. So when I first turn on limit switch 2, enable's on, done bit's on. I'm not timing yet because that doesn't happen until the timer starts accumulating, and the done bit's on immediately. This opens up. Now, if the limit switch is turned off, so now the enable is the limit switch. If the limit switch is turned off, I'm going to start timing. So here's T, right? Now I only have to time for 180 milliseconds before the done bit's going to turn off, right? So that's going to be that point right there, 180 milliseconds. If limit switch is turned off, which LEDs will be illuminated after 10 seconds? Wow, this is a little tricky here, right? They're trying to screw you up with this 10 and 180. It's 180 milliseconds, right? So if the limit switch is off, this is open now. That means that the done bit stayed on for 180 milliseconds. Timer is no longer timing because I'm beyond that, right? I'm 10 seconds. I'm way the heck over here somewhere. The done bit's off, the enable's off. Timer's not timing, done bit's not on, so I'm going to have light number 3 on. And it's going to be the same down here too. A little better question is if this would have been 10 milliseconds and 180 milliseconds. Trying to trip you up here. A lot of people will answer this and have one on here and a different one on here because they're answering it based upon this 180 being in seconds. Be careful though. Remember, our time base is in milliseconds. So the only one that's going to be on once the done bit turns off and we're no longer timing, because this will open, this will close now because the done bit's off, and that'll happen at the 180 millisecond. and 10 is way bigger than 180, and 180 seconds is way bigger than 180 milliseconds as well. So that concludes your introduction to the RS5000 software and hardware program, or excuse me, software and the actual hardware itself. And I'll get back to you in another lesson. Thanks.